So we're happy to have Renee Hlozek from Oxford. She's about to finish her doctorate. She's working with Joe Dunkley right now. And she's going to tell us all about that.
Thanks very much, and thanks for having me. Please just apologies for my voice. I would say I had a cold, but the truth is I was at a really great blues concert in Chicago over the weekend, really great, and so I was moving a little bit much in the hospital. But it's really cool to be here. It's a beautiful city, and I'm sorry I'm not here for longer, but hopefully if anyone wants to chat to me, I'd like to chat to everybody, both about the work that I'm doing on ACT. I'm also involved in other projects, kind of supernovae and things like that, so if you're interested in any of that, I'd love to chat to you as well. But I'll jump right into the talk. So this is what I've been doing with Joanna Dunkley for my PhD. I've got about a year left, so hopefully there'll be more exciting stuff to come. But of course, ACT is a large collaboration, so if you can play academic Where's Waldo, you can find my name really quickly. But obviously there's lots of different groups, including a large contingent here from CITA. So a lot of this will be familiar to you, but I thought we'd just set the stage and say, well, we talk about the CMB. Why do we use it at all? And so the way we understand it is we had, in the early universe, we had a hot, dense phase, and we have electrons and photons interacting by Thomson scattering. And in this early universe, well, we know that radiation and matter evolve with redshift as different functions. And so at some time, in the early universe, we have matter and radiation equal. And so we go from radiation domination to a period of matter domination. And sometime after that, we have the universe decouples. So it cools down enough so that you can have your ions and your electrons combining to form neutral elements, and then the radiation can free stream away. And it's this radiation that we see as the CMB that encodes, gives us some information about what the universe was like at early times. Because this happened early on in the lifetime of the universe, we believe to a greater or lesser degree that things are linear, they're clean. And so the CMB is a really clean probe of early times. We also think we have the basic elements pretty well understood. There are powerful numerical codes out there that solve the Boltzmann equations and that we can use. Then if you believe that things are isotropic, you can in fact represent the temperature fluctuations in the sky. So we can decompose them into spherical harmonics and use the coefficients of those of that expansion as our CLs and come up with the power spectrum. And that's how we come up with something like, for example, the WMAP 7-year results, which is something we've all seen. It just puts us in the mindset of getting information from these temperature CLs as a function of multipole, which of course is related to angle on the sky. And you see here we have the data points. And the cosmological model fits the data really well. Great. So I haven't said anything that's particularly new to anyone. So the question is, where does ACT fit into all of this? And the key idea is that we're probing new scales. So if we go back in time to COBE had a resolution of about 7 degrees. And to put that in context, we expect the CMB to vary on scale of about 1 degree. And so we have to wait for experiments like WMAP to really probe the anisotropies as they improve this resolution by a very large amount. Of course, Planck will do even better. We'll go from 0.3 degrees to 0.1, and we'll really resolve the fine scale structure of the CMB. But ACT takes that even further. So ACT has about an arc-minute, roughly an arc-minute resolution, and there you start to resolve not only the CMB, but all the other secondary effects. For example, we'll see the effects of X-ray clusters. They're roughly a size of about 1.4 arc-minutes to about 4 arc-minutes. And of course, you'll see point sources, which are just the size of looking at whatever frequency you're working at. And so this wealth of information, of course, we'll be able to see it in some of the other experiments, but ACT really pushes us down to high multipole and small scales so we can probe the sky with that, the microwave sky with that. So where are we? Well, ACT is the Atacama Cosmology Telescope, so it's in Hlozek, northern Chile. And the site was chosen, of course, because it's very high altitude, very dry, and so you can kind of not worry as much about contaminating effects that you would at a different location. In fact, it's so good that on a good night, me popping right out at you. Not really, of course. But it's a 6-meter all-axis Gregorian primary mirror, and has, as I said, roughly an half-minute resolution. It changes for the different frequency bands that we use, and we operate in 3 frequency channels. Now this is because ACT is designed, it's an SZ experiment. I'll go into the Sunya's voltage effect a little bit more in more detail in a couple of moments, but the key idea is that it operates at these 3 frequencies to probe both the null of the SZ effect, when you expect essentially no effect from clusters, and then to the left and the right of that. So, this is the survey that to date ACT has taken over 1.5 years of data in 3 frequency bands. But the work that I'm going to talk about today focuses on 300 square degrees, so it's not the total area that we've observed, and I'll discuss results from 2 frequency bands, 148 and 218 gigahertz. So you can see I'm going to be concentrating on the work we've done in the south rather than the work we've done on the equator, but that's going to lead to some really interesting results as well. Okay, so what do we do? I was really excited to learn a little bit more about how ACT works because I hadn't dealt with CMB data before, but one of the things that I was really excited about was to discover how we do cross-linking. So we observe mainly at night to control the systematics, like when the sun comes up, the telescope gets hot and kind of messes around with things. We observe at a fixed elevation, and the key idea is that ACT scans the sky, so it scans 6 degrees every 8 seconds. And we use a technique called cross-linking, which means that you observe every patch on the sky twice a night. So before the middle of the night, you're observing in a southwesterly direction, and then you switch over and you observe in a southeasterly direction. And so you can understand your noise properties more because you're getting 2 passes of every patch on the sky, one from this way and one from that way. And in fact, I noticed the power of this because if you take a map and you take out all the modes that are going in one direction, you can see that it looks different. That cross-linking helps you understand your noise properties and helps you reconstruct the modes really well. So we know you don't get a map out of your CMB experiment. You have to do a lot of work to get that, of course. And I'm speaking to the audience who are closest to this. This is largely done by the people here, of course. But the idea is you want to go from something that looks like that to a map. Okay, so this is your data. This is a signal as a function of time, and you can see that the signal from different detectors goes up and down. That's because they're looking through the same atmosphere, which is great to see. The problem is that on this scale, so this is 40 millikelvin, the CMB is at about 0.1 on the scale. So we want to get rid of all of this so that we can get to the signal we really care about. And it's really complicated. We have atmospheric noise that's hard to understand, and so we use the maximum likelihood estimates. I'm not going to go into the details of that, but that's done using powerful supercomputers, like exactly the ones that you have here, and you use all the computational power that you can to reduce the effective noise, to filter out the modes that are related to noise, and to reconstruct your CMB faithfully. Once you do that, you get a beautiful looking map like this. And so we need to go from that to a power spectrum. Now what we do with that is we take data which is broken into chunks, which we call time-ordered data. It's basically 15 minutes of signal. And we separate the total number of these that we'll get into 4 parts. So for each patch on the sky, you have 4 separate components. So they're separated in these chunks of data for the same patch of sky. And what we do is we cross-correlate those patches together. So they're not cross-correlated in the spatial direction, they're cross-correlated in the kind of temporal direction. The auto spectra gives us an indication of the noise in that patch. And the cross spectra, the mean of that, gives us an estimate of the power spectrum in that patch. I won't go into details about how we specifically do the power spectrum estimation. There's a lot of hard work by Amir, among others, and Steve Das, who spent a lot of energy on finding the best way to reconstruct the power spectrum. One of the big problems, of course, is that you have a strip. You don't have the whole sky with other experiments. Okay, so that's briefly just outlining how we go from a telescope to a map and a spectrum that I would use. So if you were looking at the archive in January, you would have noticed a paper releasing our first power spectrum. This was Fowler et al. And to put it in context, so here is data at that stage from various experiments like WMAP, the South Pole Telescope, and other experiments. And you see that at the high L range, at very small scales, there haven't been that many experiments to date. And then we came along and presented our first set of our first power spectrum. We had a binning in L space of about 300, and we went out to a multiple of about 8,000. Between January and now, we've been working frantically both at understanding and improving our power spectrum estimation pipeline, at understanding, working more on the noise and the systematics of how we make maps and using the data. And this is what I'm going to talk about today. So this is the Southern Survey, 2008 Southern Survey. And the reason why there are 3 power spectra here is this is the 148 cross 148. This is the 218 gigahertz cross 218, and this is the cross spectrum between them. Now, we have more noise at the higher frequency, and so for that reason, we restrict ourselves to working from L of 1,500 out to 10,000. But for the 148 gigahertz, we've been able to push ourselves down to L of 500. And that's really important because we know what the CMB looks like from experiments like WMAP at lower L, so up until L of about 2,000. And we know that we've got an ACT measurement, but the reason that the thing that's very powerful is that we overlap, and so we can link with other experiments because we overlap the same region in some range of L. Now, what we want to do is we measure response on the sky, but you want to turn that into a measurement of temperature. And there are 2 ways to do that. First of all, you can measure the temperature, you can measure the response of something whose temperature you know. And so we measure, for example, what the planets are like. You know what the planet is at the temperature, and so you can calibrate your maps in that way. And we do that. And we get a calibration error of around 7%. And another approach, which is discussed and outlined in Hygiene et al., is to take the ACT map and cross-correlate it with the WMAP. So here is the ACT strip cut out of the kind of WMAP map that you know and love. And if you smooth the maps so that they have the same resolution, you can cross-correlate them. Now, one of the cool things is that they see the same sky, which is obviously very important. And so as you cross-correlate, then you get an independent measure of the power spectrum. So here you see, here's the ACT cross ACT power spectrum and the ACT cross WMAP. We can use this to then get an indication of how we should calibrate our spectra. And we find, which is good, we find that the calibrating of Uranus and calibrating in this approach agree, but we have a smaller error bar on the WMAP calibration. This beats us down to about 2%. And so the calibration error that I'm going to be using in our power spectrum work is 2%. The way to understand the calibration error is I can shift, it basically means there's a 2% error in shifting my spectrum up or down. If you want to try and understand how that feeds through, basically I can move my power spectrum up or down by about 2%. Okay, another thing that you want to do is before you start using your power spectrum for any sort of parameter estimation or any analysis, you want to make sure that you trust it. There are many different things that happen between taking the data and turning it into cosmological parameters. And one of the things we do is we do these null tests. So first of all, I told you that we split the data up into 4 chunks. What we want to do, we know that those chunks are all the same patch on the sky, so they should have the same signal. And what you can do is you can take a difference map between 2 of them and a difference map between the others to cross-correlate that, and you should have a signal that's consistent with 0. Because if you subtract the 2 maps, you should be subtracting the same sky, so you shouldn't really get anything, any signal. And that's what we found. We found that it's basically consistent with 0. There are other tests that you can use. You can, I told you that ACT scans the sky, and so what happens is as it scans the sky, when it turns around to scan in the other direction, there's a small time when it's accelerating. We use all the data when we make our maps, but one thing we wanted to check for is, if you cut out the time when it's turning around, when it's accelerating, do you get a different map? We find that in general you don't, which is good. Of course, there are two scary error bars, which I know points which everyone notices, but in general we find it's consistent with null. You can also check the maps and the spectra you get. Do they depend on which detectors you use, where in the focal plane you are when you're taking the data? For example, does it depend on the time of night? So if you use data from the middle of the night with data from the kind of edges, dawn and dusk, do you get very different results, because we don't think you should. And this is something that took quite a few sleepless nights of my time. But these are all necessary to make sure that you trust the spectra that you put out and that you use yourself. Okay, so we've now done the test. We have a power spectrum that we believe. How are we going to model it? Because that will inform how we reconstruct parameters based on that spectrum. So we have a total microwave spectrum. We think that comes from a few components. First of all, you've got the CMB. This is the primordial CMB, the kind of thing, for example, that you would get when you run CAM. We then have a contribution from Sunyaev-Zel'dovich effect, from dusty galaxies, radio sources, and galactic emission. We've done tests to show that this is small, and so I'll ignore it effectively for the rest of my discussion. And just to put us on the same page, I'm going to be using this VL notation, which is just L plus 1 CL over 2 pi. Okay, so we look at the first term. The Sunyaev-Zel'dovich effect, in a very hand-waving, simple description, is the following. We have CMB photons leaving the surface of glass scattering on their way to us. They encounter a cluster. The gas in that cluster is hot, and so the photons are scattered off the hot electrons. And this induces a distortion in the spectrum of the photons. It's a frequency-dependent distortion, and so, as you can see from the simulation, so these are simulations from Sigala et al. 2009. And so at lower frequencies, and by low I mean kind of lower than 280 gigahertz, in this example this is 148 gigahertz, you can see that the clusters are these cold spots, these blue points. At null, at 218, you're not seeing any effect. And so I've taken the scale, you can see I've increased the numbers, because otherwise it would just be a big green patch. So there's very little effect at 218. And then at higher frequencies, this is at 277 gigahertz, the clusters are hot spots. And so that's the kind of effect that I'm talking about. Cold spots at low frequencies, effectively nothing at 218, and then hot spots at high frequencies. And so we'll include this in our model just by this factor here. If our frequency, for example, would be 1 at 148 gigahertz and 0 at 218. Great. We then have an amplitude for how big this effect is, and we have a spectrum, and I'll discuss it in a little bit more detail. We also have a contribution from the kinetic essay effect. And the way you can understand that is if you have the same photons interacting with the cluster, but now the cluster itself is moving, the photons are going to get an extra boost. For the work that we consider, the kinetic essay term will be subdominant to the thermal term, and so we can actually parameterize it by having the same amplitude. Okay, but this spectrum is important, and of course, a lot of work has been done here to say to us exactly what spectrum do we expect to see. People have different models, so this is a model from Track, Bodie, and Ostreicher, and these models basically take simulations with galaxies in them, model how we think the gas is behaving, the kind of profile, and then reconstruct a spectrum. And the key idea that we wanted to show is that given that there's some discrepancy in different spectra, it's good to include them and marginalize over them. Ideally, if we have more information, we could start to say, well, rather than assuming we have spectrum and reconstructing the amplitude, then we actually figure out what we think the shape would be directly from the data. And that's work that is being pioneered by people here. Okay. Now we have a term that's coming from the dusty galaxies. So we believe there are two components. First of all, there's just a Poisson clustering term and some amplitude. In this box here, we have just a conversion in temperature units, a conversion from antenna units to temperature units. So that's nothing really to worry about. And then we think that the sources are going to behave roughly with the power law in frequency. What is different from the Fowler analysis compared to this analysis is that we need an extra term. Poisson clustering is not enough to describe the sources. We need, in fact, a cluster term. And we detect this, the need for this at about 5 sigma. Now, that doesn't really, it makes sense, of course, because we think that the galaxies are going to be sitting in halos, and the halos will be clustered, and so having a cluster term makes sense. But the understatement of the talk is that we need more than one frequency to discern between these terms. Okay, the radio sources we just model as a Poisson term in amplitude. And as I said, one frequency is not enough. And I'll illustrate that by showing you this plot. So here, the solid white lines are using only 148 gigahertz. And you can see that the data are consistent with having no clustered components. As soon as you add in another frequency, you can start to break down the degeneracy between the two. So this on the y-axis, you've got the amount of SZ, your microcoulombs squared at L3000, and on this panel you have an infrared Poisson term and the cluster term. Of course, the clustering will also have some sort of spectrum, and different groups give different spectra to try out. We tried out two, one that's also outlined in Segal et al., and then one by students in Oxford. And we don't see too much of a difference in the amplitudes if we use different templates. They're consistent, which is good.
So is the shape of the clustering given by some halo model?
So yeah, basically it's looking at halo model and trying to figure out what kind of clustering term we expect to be has.
So you're assuming some sort of redshift distribution, you're assuming some typical mass resemblance?
Yeah, as far as I understand it. I mean, I haven't directly created them. It's not exactly my work. But yeah, that's what I understand.
Sort of a bit more phenomenological than that, but it's not really trying to say what does it actually mean. It's much more that's about power.
Like the shape, presumably we'll find some of it, things like the redshift distribution.
Not yet. Maybe.
Okay. So I'll briefly just touch on the SZ amplitude. And I showed you 4 templates for the SZ spectrum. And using these different templates, we do recover slightly different values of the amplitude. So to put these in context on this block or in the table, ASZ is related to sigma 8. And so an ASZ of 1 is a sigma 8 equals 0.8. The value that we derive is consistent with the South Pole results, for example, is being slightly lower, although it's still consistent with ASZ equals 1. But the value that you reconstruct depends on the gas physics that went into your spectrum, because we get different values of the amplitude for different spectra. What is consistent is that the total power that we have at L3000 doesn't change, which is reassuring because we think it should be consistent with the total power that we have. But of course, it's interesting to discuss these templates and to discuss that you do get different amplitudes. And as the data gets better, we would of course like to try a more template-independent approach. But for now, this is the way it went at the range. Okay, so once we break down the spectrum into these components, it's good to kind of add them all up again and see what you get. So these are the same data that I showed you before, but on one plot. So you can see, this has really helped me think about things. You can just see how you're completely dominated, or the IR really kills you, especially at high frequencies. So this is 218 gigahertz. And so, if you're thinking about estimating the SZ is way out down model is really interesting, and there's a lot more to even still to be done. Okay, I'm going to switch gears slightly. I've been discussing using multiple.
Yeah, actually, sorry.
Yeah.
Can you go back to that? Okay, like, so the difference between, like, the Poisson IR term and the cluster term is the fact that it turns flat as small l.
So the arts, yeah. So I mean the Poisson is going like L squared.
Yeah, right.
And the cluster term at large, well, it depends on your template, but at large, multiple can kind of go like L in L plus 1.
Okay, so the difference you're saying between like L squared and this cribbing thing is 5 sigma. And you can just render around like the L of 3,000.
Yeah, yeah. Is that what I'm saying? Yeah, if you only had if you only model as a Poisson term and you use all your frequencies, yeah, the difference between the spectrum that had only the Poisson and the spectrum that had Poisson and cluster would be basically the delta chi squared.
I should be seeing that.
And you know that can be absorbed by the CMP because it's
A, you have two frequencies of the CMP is black body, but also the CMP is dropping off at that range.
I can take a linear combination that cancels off the point source between 218 against 148 up or down the zone.
Well, of course, you have to model the frequency dependence, right?
Well, but you measure it. Let's take 218 over 148 positive 218 in the ratio. Let's back that off from the map itself. So then I would just say 218 over 218 squared divided by 148 cos 218. That ratio is just the scaling of frequency. And then you could just subtract 148 minus the ratio times 1.
Okay, well maybe we should talk about it more. I'd like to discuss it. I'm not sure I completely understand. I mean, let's see. What is doing it in this space? We struggle to do it in map space because you've got to worry about the beacons. The beacons are going to be different. But that's not what you're saying. You're saying just divide them out and subtract it.
That was done. And it was, in particular, that's what we were stuck with the analysis of SPT. It was not using the three simultaneously. Using the three simultaneously is far superior. So there's a lot of swap in exactly how you activate the plane zero of the whole state. I mean, the extrapolation, which is with some kind of traffic data graph.
The point is, in other words, you measure it, the ratio of each 20 is 1 for the plus 20, and then exactly that, nothing else, as long as the point for the two space the same.
Okay.
That's certainly.
But that gives you a statistically, I mean, you can only do that in the power spectrum space. If you want to do it in real space, then you have to, I mean, you're assuming that every galaxy has the same data set is mapping the same way. But it's not a perfect assumption. And it does something very complicated to your map. Because, and it's difficult to propagate data to the power spectrum space. It's easy that way. Because not all of the galaxies are the same. And it's just quantifying what it does to the power spectrum is complicated.
Okay. So this discussion about measuring the properties of the secondaries, measuring the spectral index and the amplitudes, is very useful to understand the secondary anisotropy groups. But what we also want to do is use the temperature spectrum to get a handle on cosmological parameters. Also, using combination with W hat, for example. And so in this case, what we're going to use, given that the error bars are much better and that we don't significantly add a lot if we are adding 218 gigahertz, is concentrate on 148 gigahertz spectrum. And these are consistent with lattice CDM, which is reassuring. Again, an NS of 1 is disfavored at about 3 sigma. But one of the things that we wanted to look at was not just testing standard models, but starting to probe models, non-standard models. And so that's what we wanted to look for. I won't really go over this, but we also did some checks of the likelihood assumptions themselves, but that's less interesting for now. And so when we're thinking about what models we wanted to test and what kind of analysis we wanted to do, the idea is to look at the spectrum, and when you look at it, you can kind of understand where active power is coming from. So first of all, I'm going to shift to L to the 4th CL over 2 pi. And ACT is measuring the peak from peaks 3 to 7, so it's this region that in fact is going to give us a handle on new physics. And so we're going to look for models that are going to be changing the power in the tail. So models that change the spectral index and that sort of thing. And I'll briefly outline the results. The first thing we wanted to do was detect lensing. So we know that the 2-point correlation function is not the best way to get at lensing, but it was something that we had in hand, so we started with that. And here you can see a simulation of the effect that lensing has. And it's very small. If I showed any of these individual maps to you, you wouldn't really be able to tell me if there was an effect or not. And what it does is it effectively kind of, what do they call it, the Robin Hood effect. It's smoothing out the power spectrum, smoothing out the peaks. And we find that a best fit lens spectrum is a delta chi-square of 8, based on the lens spectrum. So at around about 3 sigma, we're detecting that there's something that is smoothing out the spectrum. We decided to model this following the formulation of Calabrese et al. Where you just say, let's model, we know what, theoretically we know what the lensing power spectrum, deflection power spectrum would be. You just put in your cosmological parameters. For example, you can get a laser code like CAM. And then you can model it by an amplitude, we'll call it AL. And AL would be 1. If you had lensing, it would be 0 if you didn't need lensing. And so you can do this simple analysis, and this is what we find. So we detect AL is 1.3 plus and minus a half. These are the 2 sigma error bars, so 1.2 and minus 1.
Do you really say sigma 8 when you're doing this or something? Right. How does this work actually?
So
you're taking the linear power spectrum, using some sort of K function to get the non-linear power spectrum, you give the linear power spectrum.
So basically, it's kind of a lot simpler than that. You have your standard power spectrum, your standard likelihood, and you just say that you have another term, which is plus AL times CL55. So you're going to include distortions that would
so it's just linear lensing.
It's just saying that this parameter that's going to be a linear thing. We're not doing any sorts of complicated reconstruction or anything like that.
I mean, like for the power spectrum, one thing I thought, like much bigger, it was a non-linear power spectrum. Isn't that true?
It's not, it's a linear multiplier.
It's
a non-linear class.
Okay, so it is non-linear. Okay.
Yeah, but the way we're including it in our analysis is
yeah, that's right.
Yeah.
But the shape of the non-linear power spectrum, though, depends upon the linear power spectrum.
Yeah,
Yes.
but you're basically.
Okay, so that's my question. Yeah, okay.
Yeah.
Really simple.
But you're fixing sigma 8 and you're fixing.
we're putting it in at the same time as the other as this in the 6 standard parameters.
If you look at the figure, that one CL figure, if you go back one,
Sure.
or wherever it was, you see it's not a really big effect. So it was.
If you're bending the attention, you want to.
Yeah, well, we did exactly the same thing with that part.
Oh, you're not bending the
Well,
Well, we did, and
attention. This is active and fine.
okay, so can you be more conservative? ACT is showing a slight preference for something that would smooth the spectrum out in a way that might be distorted. But that doesn't fit in my so
Sort of doesn't fit.
Say that again.
3 sigma. It's less than 3 sigma.
it's less than, less than 3 sigma. But it's acts detected or acts as sensing a preference for something that's smoothing out the spectrum in a way that would be done by Metro in the simplest prescription. I mean, as the data improves, we're going to do this properly, right? We're going to actually reconstruct what we think the deflection house spectrum is and do the cosmology for that. But this is just given that we have a spectrum, then we could smooth it out. Can we take that? It's really, it's simple. Maybe I should change the title, but it's a really simple description. The one thing that's happening is even though it's something small, we still want to say, well, is there something in our analysis pipeline that we've done the same thing? That we've smoothed out the peaks in a way that would give us spurious marginal detection of something that looks like lensing. And so I took an unlensed simulation that we know has no lensing in the map, ran it through the pipeline in the same way, and reconstructed the value of AL, and we get an amplitude that's consistent with 0. Of course, I could have done this 1,000 times to show that 1,000 times it gives you something consistent with 0, but in something that we know there's no lensing, we don't detect AL consistent with 0, which is reassuring.
So with bunching error, can we generate something similar to the sort of suppression of
I think so, but it would have to be quite a complicated pointing error, but I think anything that's going to move things around a little bit would potentially do that.
Okay, yeah. But you're saying here presumably doesn't have a touch point. The simulation, I guess, doesn't have a pointing error that sort of like error comes of this.
In fact, it's one there. It's definitely the entry is so tested with the differences.
Yeah.
And we think we have a point error.
Oh, sure, yeah.
But yeah.
I'm just trying to think of like crazy things that might also suppress the.
Yeah.
The degree, I mean, an interesting question is, can you actually detect that there is a degree of smoothing which changes as you go to higher up? That is something which is not, it's only essentially a temporal matter. It's not something that's actually going to do a lot of interesting lower L and higher L interaction.
Yeah, the 4 point
Why
is a better way of doing it. I totally agree.
Oh, no, I'm not talking about anything sophisticated. I'm just talking about a phenomenology which this first order thing to do beyond an amplitude. It could be something about you get more at a higher L and a lesser L, and you get to smoothing.
Yeah, which is something to look at. Okay. And then some of the models that are interesting to probe because they change the high L spectrum, of course, one of them would be looking at our models of inflation. We know that standard inflation is what's seeding the structure that we see today, and standard models suggest zero running. By running, I mean a change in the spectral index as a function of scale. So that was something to search for. And what we find is that we have a slight detection of negative running. So this is the kind of NS equals 1 low running point. We know that we have a preference for NS less than 1, but the value of the running that we detect is consistent with 0. So the blue contours are WMAP only, and the purple contours are WMAP plus F. This is, of course, interesting because as we beat the error bars down, you can then start to rule out models. For example, models with positive running are now disfavored slightly more strongly than just with WMAP, but that starts to become interesting as you start to close the space. You then can start to look at different inflationary models and how it fits in the context of the data. And again, it's the high L range that's giving us the handle of this. So this is just a schematic to show you a model. Say this is NS of minus 0.75, a model that's disfavored by the data. And you can see that it's exactly this the fact that you have suppression of the power at high altitude scale, where that is where the detection power is coming from. In fact. You can also say, well, do we detect R, the intensity-to-scalar ratio, and that will give us some understanding of things like, for example, gravitational waves. So where the ratio is between the amplitude of the detector modes to the scalar modes. Now, in the past, you had to rely on CMB plus other probes to give us a competitive handle on the value of R. And where ACT power is coming from is that it's, again, constraining NS. So it's breaking the degeneracy between the the spectral index and R. And so with the CMB alone, we can tighten constraints on this RNS and RNS plane. If you go a little bit further and you say, let me assume specific inflationary potential, just something like V going like 5 to the P, then for a certain number of E-foldings, again, you assume something like 60 E-foldings, you can start to rule out models, say, P greater than 3. And so, modulo your assumptions, it becomes interesting because now we can look at which models of inflation are no longer allowed by the data, because that, again, is the holy grail to rule out non-standard models and standard ones, of course, as well.
So chaotic inflation is all that.
I mean, this is just single, yeah, simple.
So 5 and 4 was a much outdated rule that it doesn't
Already.
and this is inching down from 5 to
Yeah.
but 5 squared is sort of the
Still.
Yukon doctrine.
Okay. We then decided to look for relativistic species. Now, the way we're sensitive to any relativistic species is through the contribution to energy density at any times. Because what we're probing is, at this time of recombination, if you have species that are active relativistically, they're going to wash out power in the tail, but also you're going to change, the perturbations are going to change effectively the stance of your universe, and you're actually going to be shifting the peaks. So ACT not only gets at it from this damping tail, but you can see again, this is a schematic where I'm just making effective number of species 10, which is really large. But you can see there's a slight shift in the peaks. And so it's the fact that we can resolve positions of all these peaks and we can measure for the damping that gives us power, rather than only relying on how you can see the change in the ratio of the quantity. And ACT detects effective number of species of 5.3 plus or minus 1.3. So if you compare to the marginalized 1D line here from W map alone, we are now bounding the value from above. It's slightly higher than the concordance value. Just to put it in context, so we've got 3 neutrino species over 3.04, but the change in chi-squared from our best point to 3.04 is not large. So it's interesting, and I think as we've done our error bars and as we change things, it will become a model to test. But there's a slight tension that I think nothing to get too scared about. But this just goes to show that just adding these high L multiples to our analysis starts to mean we can get a handle on interesting questions, where before we only had upper limits.
So the effect, the effect is to just move everything uniformly, or is it?
It's going to be moving. Yes, it's going to move the peaks consistently because it's also changing.
Some scale. Oh no, okay, I see what you're doing.
The damping, of course.
So it's changing like the time of matter radiation, all of these ideas.
Yeah. So you've got the damping and
Okay,
that
so if I
change.
change the distance to our scattering surface, wouldn't it do the same thing?
Well, that's already constrained. If we just look at that of course would be really constrained by the lower peaks, but that's not answering the question. My feeling is no, but I don't have a concrete answer for you because in my head the distance to last scattering
question?
Could you counter effect this effect just by changing the distance to our scattering?
Distance or L sound?
Well, like when you
L sound would be look at the distance to the Y. I bet it does. But it's pretty much, anyway, let's move to the question.
It's worth bearing in mind, of course, that the effects that I'm showing you are all doing a similar thing. They're all kind of damping the cloud spectrum. And another one that we decided to look at, of course, was primordial helium. So these are all effects happening early on, and you could say, well, okay, so what if big bang distance is strange? We have constraints from BN from early times, but the CMB gives you another constraint to redshift of about 1,000 as to what we think the primordial helium fraction would be. And the way to understand that is, if you have more helium, then what you're doing is, as things recombine, you're actually pulling electrons out of the plasma. The more electrons you pull out of the plasma, the longer the mean half of the protons is, and so you're going to wash out structure. And damp out the tails. And so that's what we see. So again, we have a slight preference for high value of primordial helium. This is the concordance, and this is the act plus W max bound. One of the cool things, we rule out no primordial helium at greater than 6 sigma, which of course we know we have helium, so that's good. But this is giving us another handle at things at early times and the kind of composition of either is there. As I said before, each one of these parameters is going to has similar effects on the high L spectrum. And so one of the things, of course, is to say, well, are they degenerate with each other? So this is the effective number of relativistic species against the primordial helium. And if we change things together, then you see that the kind of concordance value is now within 1 sigma. So it's what just on boundary. If you vary everything at the same time, of course, you kind of wash out constraints on anything because you make variables bigger every time you add a parameter. But it's interesting to note that there is this degeneracy between all these various things that are going to be damping down structure.
So I fixed deuterium, though, I guess presumably, this curve will be quite different, right?
Yeah, because then you're actually messing up the ratio.
Right. So here you're varying, I guess, like what, like with n at, I guess, and data, plus n at and data to get 1 here, something like that, right?
Well, yeah, you could relate them effectively. So I don't have the equation, but we actually put in YP effectively, like directly.
Oh, you put in, it's not predicted,
It's a parameter that I'm varying.
Yeah, that's right. But the EM prediction, though, the actual prediction you're going to get
So you're saying a fixed deuterium?
Right, so deuterium, so if I vary NF, but I will fix deuterium, that'll also change, you might be at this differently, right? You're changing the data correspondingly, right? And deuterium pressure is very low.
Yeah. I see what you mean. So you're saying you're actually kind of mixing, you're actually confusing it. Also, you could be confusing the two things. That's, yeah, I'd like to chat to you a bit more. Interesting. Maybe
Oh, sorry, yeah.
No, but yeah.
What's your question? Your question is that BBN prediction should be a fuzzier line. Is that what you mean?
Well,
because
that line might not be right.
Well, an effective YP is exactly just using the CMB data with those as the extra variables. We know
Yes,
that
for your
one, right?
CMB
So,
prediction, that's right.
but
the
BBN will have
is-
fuzziness. I agree with that,
Yeah.
and that's interesting to do. But that's just some kind of band.
It would just be interesting to know how wide, I suppose that's how wide is the band in that thing. Yeah.
What's the thing? The bandwidth, I guess, comes from like eta being uncertainty, right? The eta is fixed by deuterium pretty well, right?
Actually, eta is the issue.
That's the
Because
method.
eta is related to gamma cubing in baryon. It's not related to the total entropy. It's got two measurables. It's not eta.
What's the main thing controlling like
It's omega BH squared is really well determined.
from deuterium, yeah.
That's from CMB. CMB determines it better. Omega BH squared? Sure. Even if you vary these things, omega BH squared is really well determined. Error bars from CMB, the primordial nucleus sequences. Right? That was the boomerang story, except for the first year.
Except that was wrong.
Yeah. No, the second. Well, no, I mean, it's the whole story. That we do very well on omega BH squared.
Eventually, yeah.
Okay, in the interest of time, I'll move on. Lastly, in the interest of checking interesting models, you can say, okay, we know that cosmic strings are not the CMB. They can't explain the solution of the C, but could there possibly be a contribution to the total power that's coming from cosmic strings? Now, I will have to plead ignorance and say that how we actually go from your particular string model to a template for your dependence multiple, I couldn't sit down and do the calculations for you. I hope that will change. But if you take a string spectrum, in this case it's a random string spectrum that we've got that's been used in the Batty and mass analysis, for example, then the contribution to the power spectrum will go as a function of the string tension, G mu squared. And so in a simple way, then you can just say, well, we add in the string template, just as we did for the case there with that, and measure this amplitude. So the two curves, to show you, this is the bound that we had before from the Batty and mass analysis. And now reduces that bound and constrains more tightly the value of the string tension. If you have your particular string template and you'd like us to give it a go, of course, please contact me. The details of this, it's always interesting to try different models, but this starts to give us a handle as to how much could cosmic strings be in the early universe. And again, we get that because they're going to be changing the energy density at early times. Okay, now, the stuff that I've been talking about up until now has been work that I've been directly involved in the power spectrum and in the parameter estimation. But of course, ACT is doing a lot of exciting things, and I'll just highlight some of them for you because I think that there's a lot of great stuff to be coming out. One of them, of course, is clusters. ACT was built as an experiment designed to detect clusters through the SX signature. And so using the 148 GHz maps, we detect 22 clusters, 10 of which are new, and this is coming up in the Marriage et al. Paper to be released shortly. So give that a look. It's always good to both confirm clusters and let me know are there and to see new ones in a blind search. But what you want to do is not just find them in your CMB map, you want to confirm them using optical surveys. And of course, we have a substantial program of observing them both in optical, X-ray, across the wavelength range already. And so these clusters are described in Menonto et al. 2010. And I really got excited about this because you can see the lensing arcs, and I thought that was really, really neat. And we're sensitive to a whole range of redshift. So this is going from about 0.5 to 1.
What's this scale?
Sorry?
What's this scale?
Oh, I see what you are.
22 hours. Okay.
Yeah.
Nice.
And then once you have these clusters, eventually you do cosmology with the clusters. Again, this is a paper that's coming out very soon. It's Segal et al. And I just wanted to put this plot up because it illustrates an interesting point. So we've been discussing in the last while detecting deviations from concordance and trying to look for strange models and their effect on the CME. But one of the cool things is if you take the number of clusters we see as a function of redshift and kind of fill it up, and you overplot the prediction from a sigma equals 0.8 kind of standard model, you get pretty good agreement. So this isn't fitted, this is just the kind of prediction within these two threshold values. So this is about 10 to 50% of masses, and the kind of dotted lines give you 0.6 and 0.14 on either side. Of course, we are sensitive to much higher mass clusters and clusters at higher redshift, because at low redshift, because the angular size is big and you kind of mix in with the CME signal, it's harder to detect them. But these are papers that I hope you'll check out when they come out soon. The next act, I've only been discussing results from the Southern Survey. Of course, we have a host of equatorial data and lots of programs designed to cross-correlate act with various fields, and so we expect a lot of interesting science results to be coming out. And the next exciting thing is ACTPOL. So this is just a prediction of the primary EE spectrum. I'm sorry it didn't come out that well, but you can see various experiments and the Planck prediction, at least for error bars. And I spent a lot of time in the talk discussing foregrounds and how complicated and how frustrating they are. But of course, in polarized emission, foregrounds are much less dominant, which is really useful because we can get a better handle on this whole all the way down until the tail. And these are the predictions, hopefully not too optimistic, for the upcoming ACTPOL experiment, which is due to start in a year or two. 2 years, 200 years. And this will be interesting, not only just for the primary spectrum, but again, cross-correlating the fields and detecting lensing, reconstructing the lensing using the polarized emissions will be very interesting and something that I hope to be involved in the future. So, to summarize, I told you about ACT and how it's a great CME instrument. I explained some of the nightmares and some of the joys and challenges of working with the spectrum and pulling apart what we detect from ACT. And then I outlined the parameter estimation and the kinds of things that we were looking for and that we tested. So if there are any more questions, thank you.
Any more questions?
Was it a coincidence that the ACT field followed the ridge of higher than average Southern Mountain Park?
Yes.
No one told me.
No, the only, well, there are some other fields down there. Maybe just 30 seconds on the supernova work.
Oh, yeah, sure, yeah. So the other work that I do is, again, kind of statistical analysis, but one of the things that I'm interested in is, at the moment, all the current kind of paradigm in supernova cosmology is to scan the sky using a large telescope like the Sloan and detect points on a light curve from an object that may or may not be a supernova. You then take a small 8-meter telescope, or 4 to 8-meter telescope, get a spectrum, and then know whether or not it's a 1A by looking at the slip-in absorption runs. If you have confirmation that you have a 1A, you then use it for cosmology, and that's great. But until now, that's worked because we've only had more than 2,000 supernovae in total in the world for often many years. But with surveys like the Dark Energy Survey and SST, you're going to get, a order of 10 to 100,000 supernova candidates. And so the work that I have been involved in is called BEAMS. It has nothing to do with CMB, but it's a Bayesian framework for using all your data in your large data sets, but including a measure of whether or not the data might be contaminated. So you use all the data and you've done a statistical error, but you could start to tease apart populations that are contaminated. So we have one paper outlining the method. Hopefully in the next couple of months you'll see a paper where I have finished applying it to the Sloan data set, to their first year data where they have quite a lot of photometric data that's never been used. And in using techniques like this, we can start to figure out how best to use the data from surveys like LSST, which even if they have a couple % contamination, will be severe guides in their estimation. So you want to talk about classification, supernovae, typing, statistics, or the CMB, then maybe.
Okay. There'll be cookies upstairs. Let's